All right, so we'll go ahead and start with relative dating, and we'll look at the 5 different principles of relative dating first. So the first principle that we'll cover is the principle of superposition, then the principle of original horizontality, the principle of lateral continuity, the principle of cross-cutting relationships, and finally the principle of inclusions. Okay, so a little bit of background. Nicholas Steno was one of the early geologists. He was a Danish geologist. I think he was an anatomist officially of the 17th century, so in the 1600s. He was one of the first geologists or people, I don't think he considered himself a geologist just then, to recognize a sequence of historical events within an outcrop of sedimentary rock layers. Or at least, again, he was one of the first one who recognized such a sequence and wrote about it. So he was credited for it. As he was working in the mountains in western Italy, he applied this very simple and very basic principle that we bring today. So this is the principle of superposition. Such principle states that in an undeformed sequence of sedimentary rocks, each bed is older than the one above it and is younger than the one below it. So just like you're seeing in the picture right here, we assume that this bed right here, or the stratum, is older than the one above it and is younger than the one below it. We can't see it in the picture, but we assume. So this rule also applies to rocks of other natures that were deposited at the surface, not just sedimentary rocks. So, for example, any volcanic ash beds or any lava flows, which were also deposited at the surface, follow this same rule, this same principle. Nicholas Steno is also credited with recognizing the importance of another basic principle, and this principle is the principle of original horizontality. So this principle states that layers of sediment are generally deposited in a horizontal position. Same thing goes for layers of volcanic ash, for example. Lava flows are a little bit different depending on where they flow from. But originally, most sediment and most surface deposited layers are going to be deposited in a horizontal position. So if the layers that we look at are flat, then they haven't been disturbed or deformed very much, is what the principle kind of states. So looking at the case in the upper left, this picture right here, the rocks have experienced some tilting as we're seeing them pretty much laying this way when they should be laying horizontally if they had been non-deformed. And in the case of the lower right here, they have experienced very intense deformation, obviously, as we see many folds within them. And this type of deformation, to the extent that we see, is probably due to metamorphic processes. The third principle is the principle of lateral continuity. And this principle refers to the fact that sedimentary beds originate as continuous layers that extend in all directions until they eventually grade into either a different type of sediment or until they thin out at the edge of some basin of deposition. So, using the 2 different figures that we see above, we can see this principle exemplified quite well. So you see on the top left figure most top left figure right here, how the sedimentary layers were deposited and they eventually either thin out right here or they grade into a different kind of sediment right here and are later cut by a stream right here. And we can assume that they were carved by it to create the resulting canyon, like the bottom figure again right here. Yeah. Or if we look at a real example right here in the right-hand picture, we see the Grand Canyon, and you're able to see the lateral continuity of the layers that make up the different canyon walls. So here I've extended for you 2 different stratum across the canyon that has carved through them, just like the stream had carved through the specific rocks forming the specific canyon right here. The fourth principle is the principle of cross-cutting relations, and this principle states that geologic features that cut across rocks must have formed after the rocks that they cut through. So, as you can see in the picture on the left, the dark mafic dikes, which again, remember, dikes are tabular intrusive igneous bodies. We covered that in chapter 4. So you see that these mafic dikes are cutting through the rock that is behind, the more light-colored rock. So the dikes must be younger than the rock that they cut through, right? And also, usually a zone that is right next to the dike can be seen, and this zone is a zone of baking, in which you can have a little bit of contact metamorphism due to the heat that the dike exerted upon crystallization. Okay, also on the right-hand side, you see the principle of cross-cutting relationships seen, this time not by a rock, but rather by an event. So in this case, you see a normal fault, sorry. Again, we'll cover normal faults and all type of faults in chapter 9. But you see that the rock has split the two different blocks aside. You see that this rock right here, the more purple-brown layer, used to be connected to this other side, which is the same rock type and it has the same age. But when the fault happened, they were displaced. And so, because the fault is overall cutting through the rock layers, the fault must be younger than the rock layers that it cut through. So the fifth and last principle is the principle of inclusions. This principle states that if a rock mass contains inclusions, which are basically fragments of other rocks, then that the inclusions are going to be older than the mass that they are contained within. So this happens, for example, when a magma body is flowing at depth and is less dense than the surrounding rocks, and so it's rising upwards. As it's rising upwards, its heat is basically making surrounding rocks dislodge larger pieces, larger fragments. And when these dislodged fragments come in contact with the melt, sometimes they will melt fully in order for there to be assimilation, but sometimes they won't melt. And so when the magma body crystallizes, those fragments are going to be encased within the crystallized form of the intrusive body, which is how you get inclusions within a rock. So what you're seeing here in the picture is pretty much that. You're seeing inclusions that have been incorporated within an intrusive body. And this is a picture taken in the Big Hole River area near Dillon, Montana. So a way to put this in a sort of an analogous food type, I would say, would be a chocolate chip cookie. So when you have a chocolate chip cookie, in order to make it, you need chocolate chips, and then you need like the remaining part of the mass. So the chocolate chips in our analogy are going to be the inclusions. They're going to be the fragments. And then the mix of flour, eggs, butter, etc. is going to be the surrounding magma. Okay? So you have to mix in the chocolate chips into this mix before you bake them. Once the mix gets baked with the chocolate chips within it, it becomes solid and it keeps the chocolate chips inside and in place. Analogously, the magma crystallizes, leaving the inclusions or those rock fragments in place within it. So again, chocolate chips happened before the overall baking of the chocolate chip cookie, just like the fragments must have happened and been there before the crystallization of the overall rock. Alright, so we just looked at the 5 principles of relative dating, super key, and again, used all the time, currently during fieldwork, and definitely in the past, even more so. So another very important thing to consider when looking at relative dating, when doing relative dating techniques, is the presence of time that has not been recorded through rock deposition. Or put in different words, it's the lack of rocks that represent a period of time that occurred. So sometimes there's time that is not recorded within a specific rock, meaning it seems as though it didn't happen, but yet it did happen. It's just not recorded. So this is called an unconformity, all right? So let's back up a bit and understand what an unconformity is based on what a conformity is. So a conformity happens when layers of rock have been deposited essentially without any interruption in time or by processes that have been acting upon them. So conversely, a nonconformity is going to represent a long period of time during which deposition of sediments did not occur, or during which erosion removed previously formed rocks, or both things. And then after that happened, that non-deposition or erosion, or both, there was subsequent deposition on top of it. So deposition started again. So as you can imagine, unconformities are incredibly common within the geologic rock record, and they happen all around the world. Many times the deposition of sediments has been interrupted by, again, either non-deposition and or erosion, but potentially also by changes such as climate change or something as geographically constrained as the change in the course of a stream, for example. So the reasons for unconformities to occur can be worldwide changes, or they can be geographically constrained changes. Overall, unconformities represent, again, missing data and hence represent missing time within our rock record. All right, so there are 3 types of unconformities, and their recognition helps geologists identify what intervals of time are not represented by the strata and thus are missing from the geologic record. Those types of unconformities that we're going to look at, again, those 3, are angular unconformities, disconformities, and nonconformities. And we will cover each of these in the next few slides. Okay, so let's first take a look at angular unconformities. This is probably the easiest one to recognize, as it consists of tilted or folded sedimentary rocks that are overlain by younger, more flat-lying strata. So it indicates that during a pause in deposition, a period of deformation occurred consisting of folding or tilting the strata, and later of erosion that took out part of that tilted strata or folded strata. After that happened is when the deposition resumed or started again. This diagram that you have on the left shows a possible progression for this to have happened. And then the picture on the right shows you an example of it in the real world. So you have the tilted strata. You can clearly tell that there must have been some sort of erosion of the remaining parts of that strata, and then that there was subsequent deposition of the pretty much horizontal layers on top of it.